Hello and welcome to this lesson for Chemistry 20. This is the final unit of the acid-base section of the solution acid-base unit. We're going to look at how we can actively, like in a lab setting, measure the pH of a solution, as well as what happens when we dilute solutions. So first of all, we can measure the pH using either an acid-base indicator or a pH meter. So indicators are usually a solution or a compound that actually changes color depending on the pH that it's in. It could also be dried onto a strip of paper, which is how you find litmus paper and pH paper. Litmus paper turns red or blue depending on if it's in an acidic or basic environment, red for acids, blue for bases. And then pH paper actually just turns a different color for each pH range, so it's a little more accurate. Now, indicator solutions are things like bromothymol blue, universal indicator, indigo carmine. We're going to look at the indicator solutions in just a second, but they turn a variety of colors. Universal indicator, again, like pH paper, a different color for each pH range, whereas things like bromothymol blue and indigo carmine switch between two colors where they have a middle color that's in between the two colors that they switch between. They can also be made from natural substances like tea, red cabbage juice, and grape juice. So, indicators. Here is a chart of indicators that you could be given on a test or quiz. In Chem 30, you're actually given this in your data booklet. And the way the chart works is it tells you, first of all, the name of the indicator. So for example, methyl violet, it tells you the range at which it changes color. So at 0 and, well, actually technically below 0, it would be its yellow color. That's its initial color. Once it's above 1.6, it's going to be in its blue color. And then in between 0 and 1.6, it's going to be a mix, which is its green color. Okay? So all of them are red to blue or red to yellow or colorless to pink. The red to yellow in between color would be orange. You're actually given the in-between color for bromothymol blue, but the rest you're not. And then for phenolphthalein, going colorless to pink, it would just be a light pink at its in-between color. Okay? So some of them change at really low pHs, some of them change at really high pHs. Now, you could be given a question where it just tells you, you have, let's say, methyl orange. And you're putting it in a solution of a pH of 5. What color would it be? So we know everything above 4.4 is yellow, so therefore it would be yellow. But most of the time, the type of questions you're going to be given are, I have a solution that is turning indigo carmine blue, phenol red red, and phenolphthalein pink. So if we go back to the chart, in order for indigo carmine to be blue, indigo carmine is blue. It said phenol red was red and phenolphthalein was pink. Okay, so we know in order for phenol red to be red, it has to be equal to or greater than 8.0. In order for phenolphthalein to be colorless, it also has to be equal to or greater than 10. And in order for indigo carmine to be blue, it has to be equal to or less than 11.4. Okay? So with all that information, we have to narrow it down to the smallest range. Now, it can't be 8 because it also has to be greater than 10. So the smallest range we can get it to is that it has to be above 10, below 11.4. Okay, so again, we would say the range is 10.0 to 11.4. Okay, you're not going to get an example pH, you're just going to get a range and narrowing it down to the smallest range. Now, you might not always have a top and bottom number. It might just be it has to be greater than 11.4, for example. Let's look at another example. Methyl violet is blue, orange 4 is yellow, methyl orange is red. So methyl violet is blue, orange 4 is yellow, methyl orange is red. I'm not going to remember that. Methyl violet is blue. Did it say orange 4 was yellow and methyl orange was red? I think that's what it said. So it has to be above or equal to 1.6, above or equal to 2.8, and less than or equal to 3.2. So again, narrowing it down the most I can. It can't go all the way down to 1.6 because otherwise methyl orange wouldn't be yellow. It has to also be greater than 2.8. Okay, so the narrowest range we can get it to is 2.8 to 3.2. Okay. So that's how your solution chart works. Now, pH meters are actually obviously the most accurate you can get to measuring the pH of a solution. It's like a thermometer. You stick it in the solution, it has a little electrode, and it gives you the pH reading by measuring the concentration of the hydronium ions, usually accurate to a couple decimal places. So pH meters can be really useful, but they're expensive and they're difficult to calibrate, so not as commonly used in a lab scenario. Now, what happens when you dilute an acid or a base? Dilution is another form of neutralization, and we talked about that during acid or base spills. When you add water, you are decreasing the concentration of the ions, and the pH is then going to change and go towards a neutral value. So an acid's pH is going to go up until you get to 7 if you add enough water. A base's pH is going to go down until you get to, again, 7 if you add enough water. Okay, so you are decreasing the ions in your solution, which obviously is going to change the pH because it's based on those ions. So for example, let's say you're told you have a solution of hydroiodic acid, and I'm looking for the pH of the solution. Now remember, when I have a compound, I have to write its reaction. If it's an acid, it reacts with water to form hydronium. If it's a base, it just dissociates. So I transfer my hydrogen from my acid to my water. One acid reacts with one water to make one hydronium and one iodide anion. Okay? I am given the concentration of the acid. I want to find the concentration of the hydronium ion in order to find the pH. So this is 6.2 times 10 to the negative 3 moles per liter. So the concentration of my wanted is going to be the same because my wanted over given is 1 over 1. But it's still something, if this were a written question, it's still something you'd want to show.
This is just a test to make sure the pH system's working.
Sorry, little announcement there. Okay. And if there were 2 hydronium ions, for example, being produced, my wanted over given would be 2 over 1, right? So you always have to double check and make sure you're doing the wanted over given to get the proper ion concentration. Now, in Chem 20, the strong acids, you're always going to be calculating the pH of. The ones you're going to have are always monoprotic, which means for the pH calculations, your acids will always be 1 over 1. But it's still an important step to take. Okay, so if I go negative log 6.2 times 10 to the power of negative 3, I get an answer of my pH. Now I have 2 total digits, so I want 2 decimal places in my answer. Okay, 2.21. Now we're going to dilute the solution. Okay, so diluting the solution, we're using CIVI equals CFVF. This is my initial volume, my initial concentration, and this is my final volume. Okay, so to solve for CF, it would be CIVI over VF. So my CI, 6.2 times 10 to the negative 3 moles per liter. My VI, technically we should be using liters, but you could also leave these in milliliters because they're in the same units, they would cancel. But if you don't want to have to remember when can I leave it in milliliters, when can't I, just always put it in liters. So we get a final concentration of 0.00186 moles per liter. Now, I can put that into scientific notation, 1.86. Actually, it looks like we're only allowed 2 sig digs. So I'm going to actually have to round this off at 1.9. There's only 2 digits here. Or I can leave it as 1.9 times 10 to the negative 123 moles per liter. Either way, your sig digs are fine because leading zeros don't count. So the 2 total digits you're allowed to keep in concentration are the 1.9. Okay? So this is your final concentration. Now it's asking us to find the pH now that it's been diluted. Now, notice this, very important, use your recorded answer. That means it wants you to use your rounded answer. This is a question that students will see on their unit test. If you don't use your rounded answer, you're going to get the wrong answer, okay? So now to calculate the pH, I'm going to take the negative log of that rounded answer. So 0.0019. Not 0.00186, okay? The rounded answer. So negative log 0.0019. We get a pH of 2.72. Remember again, my sig digs are its decimal places, matching the lowest total digits in the question, okay? Now, if I didn't use my rounded answer, if I used the unrounded answer, I would get 2.73, which would be wrong on a numerical response question. It has to be exact. So make sure you read very carefully. If it wants you to use your recorded answer, it means the rounded answer from the previous step. Okay? Now, does this make sense? The pH before dilution was 2.21. It's now gone up to 2.72. So that is what should happen when you dilute an acid or a base, is pH is increasing as you are neutralizing it. Okay? And I believe that is it for this lesson. Here's just a summary review again of acids and bases, how you identify if they're strong or weak. Acids, remember again, always react with water. Bases just dissociate to produce hydroxide ions. Unless they're a weak acid, then they react with water. Weak acids are negative ions and ammonia. But any ionic hydroxide is a strong base. I might have said acid before when I meant base. Weak bases are negative ions and ammonia. Strong bases are ionic hydroxides. For your acids, there's a list on your data booklet that tells you which ones are strong. The rest are weak. Okay? So that is it for the acid-base section of the solutions units. Thank you very much for watching this video.